Greetings, everyone. This is homework help for section 2.8. And first one is number 5. It says use the graph the given graph of f to estimate the intervals on which the derivative f prime is increasing or decreasing. Now, you have to be careful every time you're given a graph and you're asked about some function. You want to make sure you understand completely and clearly which graph you're looking at and which graph you're being asked about, and then the relationship between the two things. Otherwise, a lot of people make mistakes because they start assuming they know what they're looking at as opposed to really answering the question based on the fact of what they're looking at instead of what they're assuming. Anyways, we need to answer questions about f prime when f prime is increasing or decreasing, but I'm not looking at f prime, I'm looking at f. So I'm not going to look from, way over here to here and say f prime is increasing from, -2 up to a little less than 1 because this is f, and I want to know when f prime is increasing. So I need to know a connection between when f prime, the derivative of f, is increasing and f. And in this section, we made a statement. We made several of them, but the one I'm referring to, it said that if f prime is increasing, f is concave upward. So I want to look and see where this graph is concave upward. And when this graph is concave upward, that's when f prime is going to be increasing. Now, be careful with concave upward. Make sure you identify it, clearly. This graph is concave down all the way from here in through here to say somewhere right about here, maybe even here. And, the best bet is probably just to estimate it with 2. We can do that fairly safely. So then the graph goes concave up here and then eventually becomes concave down. And 4 might be a little bit shy. It might be a little bit higher up. Let's use 5 as a good estimate. It might be somewhere in between 4 and 5, but right now we're just trying to give a sense. So f prime is going to be increasing, let's say, between 2 and 5 because, and make sure you include reasoning why in your answer, because f is concave upward. Now, when f prime is decreasing, we're going to find that out because when f prime is decreasing, f is concave downward. So looking at this graph is concave downward over here and concave downward over here. I'll let you just write the intervals down. And so make sure you include reasoning in your work. Number 6 is the next one that was asked about. It says the graphs of a function f and its derivative are shown. Which is bigger, f prime of -1 or f double prime of 1? Now they don't tell you which graph is f and which one's f prime. So we're gonna have to first determine that. And so I notice here with the blue graph is negative right here, and the red graph decreases, pink or whatever color this is, decreases a little bit. And then the blue graph becomes positive through here, and the pink graph starts to increase. Blue graph becomes negative, red graph, pink graph, whatever, starts to decrease. So it looks like the function is the red graph and the blue graph is the derivative. We can double check a few things. Notice that the blue graph is increasing through here and the red graph is not positive the entire time. So the red graph cannot be the derivative of the blue graph. So the blue graph is the derivative. This is f prime and the red graph is f. And I want us to compare f prime of -1 and f double prime of 1. Now we can't see f double prime, but we should be able to tell something about f double prime from these two graphs that we have here. Well, -1 is right here, and f prime being the blue graph gives us this value right here. That's a positive number. So let's just keep that in mind for a moment, and then we'll see if we need to kind of look further into its magnitude. Now, what about f double prime of 1? Now, remember, f double prime of 1 is, or f double prime is the derivative of f prime. So if I look at 1 right here when x equals 1, it looks like the graph of f prime has a horizontal tangent line right there, which means its derivative at that point would have to be 0. And so that means f double prime of 1 is 0. And since f prime of 1 is this output right here is a positive number and this is 0, now we know which one's bigger. All right, let's move on to number 9. Says the president announces that the national deficit is increasing but at a decreasing rate. Interpret this statement in terms of a function and its derivative. This is a really good application, and especially right now with what we're going through with the pandemic, you could really listen to news broadcasts or read some news reports, however you get your news sources, through whatever social media or online app, probably. And you can see lots of references to rates and when if the rates are increasing or decreasing. In fact, I heard something the other day talking about the hospitalization rate right now, as we're experiencing the latest wave, is the hospitalization rate is increasing, and the infection rate is also increasing. Both are not good news for us in a pandemic. Anyway, let's get back to this particular example. The president announces that the national deficit is increasing. So the function we're talking about here is the national deficit. This is F. Okay, that's if you don't know what this exactly is, it doesn't really matter. It's just a measure. I'm not even sure I can define it clearly, but it's a measure of basically the debt that the country's in. It's increasing. So if the function is increasing, then I know its derivative is going to have to be greater than 0. And it's increasing at a decreasing rate. So they're talking about the rate of f prime, I'm sorry, the rate of f prime. But what is the rate of f prime? That's just the derivative of f prime. That's f double prime. And so that means at a decreasing rate, that means f prime is decreasing, which means that f double prime is going to be less than 0. So if we were to actually sketch a graph of f would have to be increasing and concave down. So it's going like this. So the president in this example here is trying to soften the blow of the fact that the national deficit is increasing by also saying that it's increasing at a decreasing rate, which means it's like this. So it's getting worse, but it's not getting worse in a bad way as it would be if it was doing this, because that means it's getting worse at an increasing rate, and then we'd really be in trouble. So he's trying to soften the blow a little bit with that decreasing rate comment. Number 12. Particles moving along a horizontal straight line. The graph of its position function, the distance to the right of a fixed point as a function of time is shown. So that's the graph we're looking at. When is the particle moving toward the right, and when is it moving toward the left? Now keep in mind, this is just a graph of the distance the object is from the fixed point. It's not the actual path. The object is not traveling actually along this curve like this, okay? So hopefully, I don't know if I can undo that. I don't see an undo button here for this, but I can erase. So this just tells us, what the particle is doing. It's moving horizontally. It's moving side to side. And so it starts at, at 0 here. So it's starting at the origin. And then, well, what's happening here? The fact that the values here of S are getting larger, that means it's getting further and further away from the starting point. So it's moving in some direction. We can say it's moving to the right. And these are time values here, so don't mind these. It's moving to the right, okay, until it hits 2 seconds, because it hits a maximum right there. What happens here? The distances start to get smaller, okay? These values over here are smaller. Like this value over here is smaller than this value over here, or this value is smaller than this value right above. So the graph is getting smaller. That means the object has to be going back towards the origin, back in this direction, okay? All the way until it goes over to here, okay? So it's going to go back for a while to here. It's not going to quite make it back to 0, okay? So it's still away from the origin. But over here, then it starts to increase again, which means it has to start moving back towards the right. I'm going to actually draw this separately here. So the object moves to the right for a little bit, and then starts to move to the left for a little bit. But when I do it on top of itself, it's hard to see. Moves to the left when uh, the graph is decreasing through here, and then when it starts to go back to increasing at 4 seconds, it goes back in this direction over here. So this is 2 seconds and this is 4 seconds, and that's what the object's doing. That's when the object's moving left and right. Okay, you should be able to get the answer based on what I just described to you. But basically what I'm looking for is to see where this graph is increasing or decreasing, because when this graph is increasing, it's moving further to the right. The object's moving further to the right. When this graph is decreasing, it's moving back towards the left. All of these statements are because the outputs are all positive here. If the outputs are negative, things could be slightly different. You should think about it, figure out what's going on. Um, when does the particle have positive acceleration? What we have here is the position function s. This is the acceleration. If you remember, we said that the derivative of the position function is the velocity function, and the second derivative of the position function, which is the first derivative of the velocity function, is acceleration. So the acceleration is the second derivative of the position function. Well, what tells us, or rather, what features of the graph tell us about the second derivative, or how does the second derivative relate to the graph? Well, in some of those statements we made in this section, if the second derivative is positive, the graph is concave upward. If the second derivative is negative, the graph is concave downward. So the acceleration is related to this graph by looking at its concavity. We want negative acceleration, or we actually want both. We want positive acceleration, so that means we want the graph to be concave up. The concavity looks like it changes here right about 3. That's a good enough approximation. So the graph's concave up on this interval, and that's when the acceleration will be positive, and concave down over here, that's when the acceleration will be negative. Let's squeeze another one into this video, number 18, which seems to be on the next page. We'll see if I have to leave the picture here. Sketch the graph of a function whose first derivative is always negative and whose second derivative is always positive. So if the first derivative is always negative, f prime is less than 0, that tells us that f is increasing. And if the second derivative is always positive, f double prime greater than 0, that tells us that f is cc up. Okay, so you need to draw a picture of a graph that is increasing and concave up. And we did that in our notes, and so I'm not going to draw it for you here. So if you can't figure out what the graph would look like if it's increasing and concave up, go look into your notes. We actually did this in a Desmos activity for section 2.8, but hopefully you put it in your notes. If you need to go look at that Desmos activity for section 2.8, feel free to go find it there too. But I remember telling a lot of you, no, your graph isn't always increasing, and no, it's not always decreasing, and whatnot. And some of you had to do a lot of little fixes, which is okay. You were still learning, and hopefully what I said is a good enough of a reminder. Let's squeeze another one on this video. Number 20. We're trying to sketch a graph of a function that satisfies all of these things here. So I'm going to actually have to get to my note-taking app, excuse me, for this so that we can see what's going on. So we want f prime greater than 0, f prime greater than 0 for all x not equal to 1. We have a vertical asymptote at x equals 1. F double prime is greater than 0. Did I read that right? Yeah, greater than 0, x less than 1, or x greater than 3. And f double prime is negative between 1 and 3. 1 less than x less than 3. All right, so we're going to squeeze all these onto a graph. And so what I would do is start by getting some axes. And then like I've shown you before, I would start dividing this up according to, whoops, I want to change that, I'm going to use that, around these points. So at 1, I'm going to draw a vertical dashed line because, well, it's actually the vertical asymptote. They told us that. I'm also going to draw some other dashed lines that I'm going to use to help sketch the rest of the picture. I need one at 3 also. I'm going to use a different color. The orange one here is the one that's going to quote unquote stay in the picture. All of these dashed lines, they're not really in the picture. They're just there to point out or have you notice something that's going on. Anyway, f prime is greater than 0 means that the graph is always increasing. So we got increasing here to here, still increasing in here, it's still increasing out over here, forever, always increasing. We got the vertical asymptote. F double prime being positive tells us the graph is concave upwards. So we got CC up over here. This is from values less than 1, and CC up greater than 3, and then CC down in between. And so now I just need to hook pieces together like we did in our notes of these different things. So increasing concave up looks something like this. It's always increasing concave up on this interval, so you can do something like this. There's lots of ways of making that true. And then this is an asymptote, remember, so it's got to be going towards that. It's going to be here increasing concave down on this interval. This one's not an asymptote, okay? So graph has to be increasing concave down, so it's going to be something like this. And again, asymptotically headed towards x equals 1. And then the last part is increasing concave up. I'll let you finish that one on your own without me. I'll make another video for the rest. Go study.